moving on to section 1.4, roots of a quadratic. Let alpha and beta, this is quite a common notation for the roots, be the roots of a quadratic. Then what you might deduce that this quadratic at some stage may have looked like this after some simplifying or dividing through by the coefficient of z squared. So if alpha and beta are the roots, they must have come from solving this equation in its factorized form. So let me expand it. That's going to be z squared minus alpha z minus beta z plus alpha times beta. And let's gather the middle term as minus alpha plus beta z plus alpha beta. So this is a really crucial result. So if you know that alpha and beta are the roots of a quadratic, then you can actually write down what quadratic that it's been solved by multiplying the two roots and putting it at the end of the equation as the constant, and adding the two roots, sticking a minus in front of it, and this is the coefficient of the middle term. Okay, so let's have a look at example 9. How can we use this kind of idea in a question? Okay, so here we've got alpha, which is 7 plus 2i, and we are told that this is one of the roots of a quadratic equation with real coefficients. So now you've been asked to state the value of the other root. Now, another very crucial result is that if you have one complex root of a quadratic equation, then you do have the other, because they are always going to go in conjugate pairs. So if alpha is one of the roots, then beta is 7 minus 2i. That's going to be also the root. Okay, so complex conjugate pairs are solutions of a quadratic equation where discriminant is less than 0. So in a situation when you know you're going to get a complex number solution, you also know the other solution. So how am I going to find this quadratic equation? Well, you can obviously use this result. It's very nice and easy. But because we are going to use it in a minute doing part C, I'm going to show you an alternative way of doing it by simply substituting these two solutions into our factorized form. So if alpha and beta are the solutions to our equation, then they must have come from doing the following. So you must have had one bracket where you had z minus 7 plus 2i, and the other bracket where you must have generated this complex conjugate as its solution. So the trick here, I mean, obviously by all means multiply those two massive brackets out carefully, but there is a quicker way of doing it. So drop those internal brackets, so z minus 7 minus 2i, and then 7 minus 7 plus 2i. And notice, what do you have here? So what we have here is two brackets multiplied together, and those two brackets have been made out of the same two terms. One has z minus 7 and and the other term is 2i. Okay, the difference of two squares. We can take z minus 7 squared minus 2i squared. There you go. Okay, so this one was our pink term, and this one is our purple term squared. So expanded, that's going to go to z squared minus 2 times 7, so it's 14z plus 7 squared, 49, and then minus 4i squared, and that's going to give you plus 4. So for the final answer, z squared minus 14z plus 53. Okay, so let's go to part C. Let's see what we get if we add the two roots. If you add the two roots, you're going to get 7 add 2i, add 7 minus 2i. That is 14. Okay, now 14 would go in here. So you would have z squared minus 14. We have got z squared minus 14. Now, if you multiply the two complex numbers together, you're going to get the difference of two squares. I've already mentioned if it's complex conjugate pair, you just do 49 minus 4i squared. So it's going to be 49 plus 4, which is 53. So this part would go at the end, and we have got 53 at the end. So I think if you learn this, and you need to learn this result, it will be quicker in generating the quadratic that the roots came out of. Okay, so it's exercise 1E that follows.